but yeah.
No, this is delightful, and I guess I'll decide whether I upload it all at once or if I chunk it into more bite-sized pieces.
Great. Yep.
Uh, but yeah, okay. So we talked about inductive predicates.
Mhm.
I basically said they're unavoidable if you want to specify a program logic, but in some sense, any logic at all, right? I'm very attached to inductive predicates. It's specifying things as, the smallest set of rules,
Mhm.
from some seed. Um, but maybe I'm biased. Maybe you have a different way of thinking about these things and why one should care about them.
Right.
Or
So yeah. So
perhaps you want
first,
to even explain what these things are, because
yeah,
I'm not
that's
sure
right.
I've
Yeah.
really done it.
So uh, when writing down, I mean, I guess we have now in our conversation talked about these inference rules on the number of occasions. So when you write down such an inference rule, the idea is again that you get the thing, the judgment below the line if you can just have those things above the line. So, but a question one might ask then is, well, okay, that's one surefire way to get it, but then is that the only way that you can get it? Maybe the judgment below the line, maybe it always holds, and it's or maybe it just usually holds, and this is just one instance of it. So so you have to be clear about that when you write down the logic. And so usually what we want there is we want the least fixed point. And we need to be careful about what it's the least fixed point of, but it's the least solution to something. It shouldn't be using these rules should be the only way of deriving these sorts of things.
Okay, so let's see. Let me try to give an example.
Mhm.
Uh, it's a boring one, but how about evenness, right?
Right.
How can you specify whether something is even? You could just say something is even if and only if,
Mhm.
and really it's only if,
Yeah.
it's zero, so
Mhm.
zero is an even number. And then if you already know that n is an even number for some arbitrary n,
Mhm.
and I'll have to do some other podcast on what it means to be arbitrary, but whatever.
Uh-huh. Yeah.
Then adding two to that number, just plus two,
Mhm.
that also gives you an even number. And what it means for it to be the least predicate is
Mhm.
basically saying these are the only ways to get an even number. It
Mhm.
has to be one of these two rules, and one of them is recursive, so it can kind of refer to itself. But then again, you to get that premise to
Mhm.
prove that original n is even, you only can apply these rules, and so eventually it's kind of intuitive to see that you'll bottom out at the axiom one, the zero.
Mhm.
And so in particular,
Mhm.
three is not even
Mhm.
because no way of applying these rules will get you a proof.
Uh-huh.
And so you can't, yeah, there's no magic way of proving that three is even. It
Mhm.
has to be done via successive applications of these rules a finite number of times.
Right. And of course one would even that to prove that three is not even, you have to do some work because what if you start with zero? Okay, it's even, so two is even, four is even, six is even. Maybe if we just continue adding two for a
Yes.
while, we'll get to three and
Yeah,
we'll
yeah, yeah. You have to
won't ever
somehow
see.
know that three is
Yeah.
not going to be in that hit set, that
Mhm.
infinite set of things you hit.
Right. Well, by the way, and you were assuming natural numbers here. So if we had integers instead, and we were trying to prove that something was even,
Yeah.
by the way, first of all, there's a different. You can also the way that you described it is like zero and then the plus two case. So you're going sort of upwards. It that probably has some name, but whatever it is. But you could also imagine going downwards, like evaluating, like if you say, is n even? And then I'm going to check, is it zero? Okay, then I'm going to say no. And I mean, so I'm going to say yes, rather.
Yeah.
And then if not, I'm gonna check if n minus 2 is even. So I mean, if we do it in that downward direction, well, if we have the natural numbers, we have to be careful so we don't subtract 2 from 1. But otherwise, if we're dealing with the integers, one might then say, well, is -3, is that even? Well, in that case, we have to check, is -5 even? And is
Yeah.
-7
Now
even, and so
you're
forth.
running away and
Right,
you don't even know, like, am I ever going to bottom out? You have to sort of,
exactly. So if we have that kind of setup, then if we want the least fixed point, the inductive sort of meaning of these things, then -3 would never be considered to be even. But a different thing would be to say, well, we want a co-inductive solution. We want the greatest solution, or greatest fixed points of these things. In that case, that would mean that unless you could do something that's going to contradict what I said, then it is true. So in other words, it's the largest, the thing that's true as often
yeah,
as it could
as
possibly be.
permissive as it can possibly be.
Exactly. And usually when we write these inference rules, uh, usually we want the least, we want the inductive one.
Yeah, because we want to, yeah, somehow we want to be strict. We're the I can't find a good metaphor here, but we're the enforcer. We
Right.
want to make sure that the program behaves, and
Mhm.
therefore, we have to be the least permissive possible while still, having these rules.
Right. So, and by the way, the notation that is sometimes used in papers, if you have the co-inductive one, is that you write a double line instead of a single line.
Mm,
I don't know if that's a good convention or not, but I think I've seen that used. I've used it myself also.
interesting.
That kind of
It's used for other things, unfortunately,
okay. Yeah,
but it's
probably
kind of
is.
hard. If you only have lines to work with, I mean, it's kind of hard to
That's right.
come up with that many things.
Yeah. So now if you, I mean, if we want to, so usually then, I mean, I mean, it's the least one that we want. And if you want to work with these things, then suppose, and let's take the even example, and let's say that we're over the natural numbers so that it's, we don't have to worry about the negatives perhaps, but if we have a situation like that, there are two things that you might want to do with such a predicate, with the even predicate. One is that you want to establish that it holds, and the other one is that someone else has established that it holds, and now you want to prove a consequence of this thing. That is, someone gives it to you. So establishing that an inductive predicate, that the least predicate holds, is easy in the sense that in for your example, we start with 0 and then we build it up, and we build it up to the number like 18 that we want, and so we're going to have
I thought you were going to say the opposite. I thought you were
oh
say you start with 18 and then you try and figure out how you can fit that 18 into the bottom of some rule, and then you keep doing that until you run out
ah
of.
I see. Okay, sure, right. Actually, yeah, it's also fine. But what you get is there's a sequence of sort of inferences that you can lay down, however, whichever direction you write them. Um, that then says, well, 0 is even, and therefore so is 2, and therefore so is 4, and so forth until you get to 18. And actually, this also would hold for the co-inductive rule. That is, if you want to establish something sort of conductively, if you want to do it for 18, you could do it the same way. I mean,
Sure.
um, so now going back to the inductive one, if we want to use it, if you're telling me that you have established the evenness of n, and then I want to prove something about it, maybe I want to prove that um, I don't know, that n plus 1 is odd, or something. Oh, thank you very much. Am I getting lunch? Yeah. Thank you. Nice. Um,
That is
uh,
nice.
right. Scientists have to eat as well, then.
We're just like ordinary people.
Exactly right. Yeah. So,
Right,
so
right. So you have a co-inductive thing, and
mhm.
we've noted that, in the co-inductive presentation, like actually, I guess 3 is even, or is that true? Let's see.
It- yes. So well, depending on how we state things, if we didn't, if we consider the integers, I Probably yes. That is, if we take
Yes,
the
yes.
same definition, if we say 0 is even, and so if something is even, then that thing plus 2 is also even. In that case, I mean, 3 would, I mean, that it doesn't 3 doesn't violate any rule. So,
Right, right. You
so
can sort of build this infinite chain that goes backwards
right,
to minus infinity or whatever.
that's right.
And that's fine. That's just a
That's
fine
fine.
co-inductive
Right.
line of reasoning.
So establishing it, so establishing an inductive predicate, that is, the only way you can do it is you build up this in sequence, the long inference of things. For a co-inductive one, it gets tricky because if we want to, I mean, because we're going to have like an infinite sequence of inferences. I mean, that is, as we said, I mean, you go from 3 and I mean, we're never going to get anything that contradicts it, but we somehow
Yes.
we need to deal with that. Now, if we want to prove something from it, it goes just the other way around. So if you want to prove something from a, let's say now a co-inductive predicate, so someone tells us that that n is even, um, well, I mean, then we can use the rules I mean, we can prove consequences of that, because we know then, for example, if n is even, then either it was 0 or 2 smaller than it was also even. But if we want to, and we would, because you couldn't ever, well, but in the inductive case, if you start off with something, then you often need to know that it really is the least, um, because let's say that we want to prove inductively that 3 is not even. That is, if you give me n, if you say that n is even, then I'm going to prove to you that n is not equal to 3. And I would prove that by, well, induction, which not coincidentally has the same name, but we're then going to see, well, is n, I mean, there are two possibilities for n. Either it was 0, well, in that case, certainly it wasn't 3. Or if it was something plus 2, then, well, then in our case, then 1 would have had to have been even
Yeah.
as well.
Yeah.
And we go
And
from there.
then there we can repeat, and then
Uh,
like somehow we get that one is not anything plus two,
that's right. And then we're done.
then we're done.
So, so, so if you want to establish an inductive predicate, that's sort of easy, or easy in that you, I mean, you just follow. If you establish a predicate, if you have established it, it doesn't matter. I mean, if you have the long sequence of inferences, then that's the same for inductive or co-inductive. But for co-inductive, it's more tricky to establish things when things are infinite, and it goes the other way around when you want to learn something from a predicate that someone has that's described. But let's go back to the inductive one. And actually, I guess everything we're going to talk about here is the same things hold if you just I mean, flip your head the other way around or flip the lattice, whatever. Um, and so if we have an inductive predicate, something that I struggled with for some time actually was I wanted to incorporate inductive predicates into Dafny, and they had some different names to begin with. They're now called least predicates. And Dafny also has greatest predicates, so it also has the co-inductive ones. And so, so if you want to introduce that, the question I had was, if you want the ability for a least predicate, for an inductive predicate, so that you can do induction like on kind of the predicate itself, that you know that if someone established this thing, they either established it because n was 0 or because it was 2 greater than something else that they had already established it for. So so you want to be able to, I mean, somehow do induction on this predicate, but if you think a predicate is just a function, it's a function to Booleans, if you have that view, then I mean, how do you do induction on a function? A function is just there. It's so another
Yeah.
example that might be useful would be, um, let's say, if our rules were just, if we define a least predicate p on a natural number n, and we say p of n holds if p of n holds. In other words, it holds if it already holds. Well, in the least semantics, the inductive case, this is just false because there's no finite inference that will be able to prove it to you. But in the co-inductive case, it's always true.
Yeah, yeah.
So
So
if you
so this
want to
is empty, the empty predicate, right?
exactly, right. So if you now wanted to prove something about this, like for example, someone tells you, I have proved, I mean, here's P of n, or from the fact that P of n would hold, prove that n is not equal to 3. Well, if we're going to do that, we're going to then look at the rule and say, well, there's only one rule. So evidently, um, I mean, this must have come from using that one rule. So what's above the rule is again P of 3. So then we would kind of somehow recursively call the lemma on the same thing. That this doesn't seem to make sense. So so what I struggled with was like, if you have an inductive predicate, is it a function like that? Because if it's a function, then how can you possibly do induction on it?
Right. Yeah.
And but if it's not the function, maybe it's data. Maybe it's like that. What when you talk about P of 3 or whatever it is, what you're really talking about is it's a data structure that underneath it has a proof. It's a finite data structure with that
Hmm.
proof, with the
Like a
inferences.
tree-like thing.
Exactly, like the tree-like thing. And so if you choose that, then it's kind of dicey. Now, if you have a data structure that you could use in the program logic, I mean, for example, the precondition of a method can now be a data structure. I mean, isn't it supposed to be a Boolean or a predicate?
Yeah,
And
yeah, yeah.
this bothered me for some time.
Yeah, and let's see. One thing that occurs to me is this even predicate.
Mhm,
You can use if you could do induction on it. You can use it to define the divide by two function, right?
mhm,
In which
right,
case, if it's you look at the proof, if
mhm,
it's the zero proof, then you just return the number zero. So you're doing
mhm,
this weird thing where you're taking a proof and building an integer from it. And then if it's the n plus 2 case, right, then
mhm,
you take the number you got from the premise
mhm.
and then you add 1 to it.
Ah,
And
because it's because you use one more inference step somehow.
yes, yes.
Right, yep, right.
Yeah, and that is the function which takes in a number, a proof that a number is even, and returns the number divided by 2,
Hmm.
right? So
Right.
this is extra, yeah, this is extra confusing because you're going from proof world to data world, like
Ah, right.
actually.
Yep. So I think, I mean, I wonder if I think, I mean, it would be lovely if this was as deep as like is light particles or
Yeah.
waves or something like that, right? But I suspect it's
Well,
not quite. But it's
I mean,
some kind
I
of,
don't know, right? You mentioned the calculus of constructions in
Mhm.
that paper
Yeah.
whose name is Well-Founded Functions and Extreme Predicates in Dafny: a tutorial.
Mhm.
And in the calculus constructions, right? This at least originally
Mhm.
the philosophy held true. Like a proof was really a data structure, and that thing is very, very uh, philosophically foundational
Mhm.
in in the original conception of the calculus of constructions. And
Right.
so I don't know if it's as deep as quantum physics, but it's definitely
Mhm.
people took this analogy very seriously.
Right. And I think I mean, it makes sense right. And so many things have been built on top of that and so forth. And it very nicely mimics these or encodes these I mean, inference rules that we've talked about now several times. So yeah, I so in Daphne, it's not the data structure. So
Right.
I guess maybe that's a big interesting thing
So
here.
what
But
happens in Daphne?
yeah, right. So in in Daphne actually for every predicate, let's call it P again. So P is then defined, let's say, to be the um, the inductive predicate, and this is a little bit easier to look at on in print. I mean, that is to say what it is, but it's the least when you define. Let me try. Um, if you define the
Yeah,
predicate P of X to be equal to something, then essentially you've written down on paper an equality that the left-hand side is p of x, and the right-hand side is something that is probably also going to mention p in some way, um, which we think of as sort of a recursive call. And of course, this is supposed to hold for all x, so we could also shuffle things around to say, to leave just p on the left-hand side. And so p is equal to, and then on the right-hand side, it would be like a lambda. So it would be p is equal to the lambda x, blah, blah, blah. And then in the blah, 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 there are occurrences of p. So one thing that we want from such a definition, I mean, anytime at all that you write down a mathematical equation by sort of definition, and the same symbol occurs on both sides of the equality, I mean, you should be nervous, and we are, right? And one way that you can be rest assured that this is good is if it is Boolean and the symbol in this case p occurs in positive positions on the right-hand side, then things are fine. And that's something we know from the Knaster-Tarski theorem, fixed points. So monotonicity there is essentially is good. Luckily, just about all such things that we would write down are monotonic. That's not true if you're doing logical programming and
Yes,
stuff.
yes, yes, yes.
But
So, okay, man, there's so much to say here, right? Because this lack of monotonicity is one crucial ingredient of various paradoxes. Like there's this thing called the Curry paradox, and I like to talk about these because who doesn't love paradoxes, I guess.
Exactly. Yeah.
And so yeah, so the fact that you can have fixed points that don't satisfy this condition,
Mhm.
it means your logic is in trouble, of course.
Right.
Uh,
Yeah.
and
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 people, yeah, anyhow. So, okay. So we take monotonicity sort of for granted in these sorts of things. So now so when we talk about least and greatest, and I've said fixed points and solutions, what I mean then is, I mean, we can be precise about it to say that if we want the least semantics, the sort of inductive predicate, then it is there could be several p's that satisfy this thing. And we know from the Knaster-Tarski theorem that there is a least and a greatest. And least and greatest meaning that if you think of P as a predicate, and which is then a pointwise extension of the Boolean lattice, and which has a top and bottom, but it has a least and greatest.
right, okay. So I feel like the need to clarify here.
Okay, yep,
This lattice is the set of all subsets of, your terms or whatever things you're predicated over. If we're talking about even numbers, then you look at the set of all subsets of the natural numbers,
right.
which I guess we actually talked about last time on this podcast because we talked
Mhm.
about filters.
Yeah,
But this, I mean, this is an ordered set, and the order is just inclusion, right?
that's right.
A set is bigger than the other if it's actually contains, right? So
That's right.
so so nothing too mysterious is happening here.
Exactly. And yeah, thanks for bringing that out. It's the inclusion, which means that the type of that X doesn't matter if it's even numbers or if it's real numbers or whatever it is. It's the inclusion of saying when the predicate holds or not. That's
Right.
the thing where we get the least and greatest from. So yeah, so in Dafny then the when you're allowed to define least and greatest predicates, and essentially you define it as I said, like p is equal to lambda x of something, but actually you don't say the lambda, you say p of x, and then you give a body for it. But it's and Daphne is going to check that things are monotonic, um, and and then, well, so now what happens? Well, now you have a predicate, and this predicate is nice because you can use it wherever you would need a Boolean expression. For example, we don't have the strange situation of putting like a data type, a value, some data structure somehow into a precondition. But
Sure.
then, and then to prove that it holds for an inductive one, well, that's also sort of easy because we said earlier that it does to establish, if you want to establish an inductive predicate, well, you have to start from some base case that you find, and you have to give a sequence of things that show it. So that holds true here as well. There's nothing special actually in that case. So the special thing comes when someone has told you that P of n holds, and now you want to do essentially induction over that derivation. And the way that it's going to happen in Dafny is that essentially you do derivation, you do induction over the height of that derivation. But where does this come from? Well, the way that it's defined is that if you have a predicate P, let's say P of X, that is a least predicate, then Dafny also defines, when you declare such a thing in the Dafny program text, it also defines another predicate that I call the prefix predicate. This term comes from, well, I don't know, I'm surely I learned it from some publication from Patrick and Randia Cousseau, but I'm not sure right now. But anyhow, but I call it prefix predicate. And the prefix predicate is written P hash in syntactically. But so the prefix predicate takes two arguments. It, in addition to the argument of the original predicate, the least predicate, X, it takes another one that I usually call K, and K is essentially the height. So now what you can do is you can define the prefix predicate, so P hash of 0, comma X. Actually, we can even drop the X part for this discussion since it's hard to keep symbols. But if we talk about the prefix predicate P hash, then if we have P hash of 0, that is going to be false. That is, and because there's no proof of the predicate P that has 0 levels.
Right.
And then P hash of 1 is going to be, well, whatever that right-hand side was in the first place that had the lambda, but where every sort of recursive call has been replaced by P hash of 0. And then you continue this way. So P hash of n plus 1 is the right-hand side where all of the recursive calls have P hash n. And now it turns out that what you now get is, well, there's going to be a footnote, but what you now get is that the original predicate P of X, and I guess I'm saying X again, the original predicate P of X holds if and only if there exists a K such that P hash of KX holds. So in other words, there exists some height at which you have derived the predicate. So the proof there.
Right. So we've taken this kind of circular definition, right?
Yeah.
And we've broken the circularity by introducing this height and having
Exactly.
it
That's right. And
kind of count.
and that height is just a natural number, so we know how to deal with it with induction and so forth. But there's a footnote, and I think it's an interesting one because the way, I mean, you refer to that paper, which again has extreme predicates. So I call it extreme predicates, meaning least or greatest. That's what extreme means in this case.
Sure.
I wonder, by the way, it's kind of interesting. It seems like in math and computer science, we never want anything but the least and greatest fixed point. We never want like the fifth fixed point and then to the right a little bit to kind of fixed point.
Okay. Spoiler alert. I've also recorded another podcast that I haven't yet published that talks about something called the Veblen hierarchy, that where you actually you take a function and then you enumerate its fixed points. And that turns out like if in certain cases on functions over ordinals, the sequence of fixed points is itself like or in the ordinals. And so you can you can count those. And indeed, you're not taking specifically the fifth, but you are at least looking at this whole family instead of just.
Interesting. I'll be very interesting in checking that out when it comes out. Yeah. So right. So we have the least and greatest and this, so another question is this number, I mean, it was a natural number. I said that the index of it, the height of it is a natural number. And if we think of it as a proof, that's what it would kind of look like. Well, it turns out that if you have that, if you define it in this way, then by a theorem that was by Kleene, so there's the Kleene fixed point theorem says that you can do just exactly the construction that I said. If the predicate is not just monotonic, or the predicate, the functor kind of that spells out this thing, is not just monotonic, but it is also continuous. And continuous means that it distributes over chains of things. So Dafny does such a check, and it checks that syntactically to see if it falls within something that can be allowable, and then you get to do this, and it works for inductive ones by then it's the definition that there exists a k, there exists a height, and if you do the co-inductive ones, then it says for all heights. So it's actually very nice. It's easy to support both least and greatest.
Right, just
Right.
swap.
That's right. You just swap. It really is, which is beautiful. And actually, um, it turns out that I had, well, I'm going to get to extending it beyond the natural numbers, but let me, as a parenthesis, when at some point I had gotten interested in these conductive sorts of things, and I think I mean it was some situation I was sort of unhappy with management at my employer at the time, and because we had to do all these things that were going to connect to products, and it seemed so short term, and I'm like, well, okay, if that's what we're going to do, I'm going to do something completely opposite. I mean, co-induction seems like something so useless. I'm going to just try to do something with that. Of course, it's not useless, but at least it was not. It's not what anyone was asking for in the program verifier at the time. But it seemed to make it good to explore. So Michał Moscow and I explored this, and we set up this. So we did what the construction that I was telling you about here for co-inductive things. So essentially, we had the greatest predicates, and so I mean it's funny and somewhat embarrassing that a few years later, when I thought I really should roll in inductive predicates somehow, and how am I going to do it? And then when I realized this is how I'm going to do it, then I realized, of course, it's already there. So it took me an afternoon to add. I mean, because Michał and I had already added.
That's funny.
Yeah, I don't know why
It's
that didn't dawn on me. If, yeah.
no,
So
it's funny. It's also funny that you started with the more esoteric one, in my
yeah, that's
opinion.
right. Yeah, right. So, okay, so now going back to the natural number. So Michał and I, and from the beginning there, I mean, we had this continuity restriction and usually that's not much of a problem, but it is a problem if you're trying to do a co-inductive program semantics. That is, if you want to use these things to define a co-inductive big step semantics, for example, of programs. And maybe let's not go into that. I mean,
Sure,
what that is.
sure.
But for the sequential case, it turns out that you get an existential quantifier above this double line, if we use the double line for the
Hmm.
co-inductive one. And so there's a recursive call inside of an existential, unbounded existential quantifier, and that turns out that makes it not continuous, and that's a bother. So, well, then it turns out that there's a lovely paper by Patrick and Radia Kuso from 1978. So right around, I mean, the other 77, 78, 79 papers that they wrote that were just so famous. But there's a paper that's much less known that they wrote in 78 about it's called something like computing fixed points or something like that. I don't remember what it's called, but what they show is something that would seem like, I mean, people in the 30s when they studied lots of lattices would also have known, but I have also looked and have not seen the actual results, at least written down. I think that
That's
this
funny.
paper.
I bet I know what result you're talking about, and
Uh-huh.
because my PhD was on termination analysis of higher
Ah,
order programs,
oh, lovely.
and
No?
yeah, indeed, the result you're about to mention is basically folklore, where it's sort of
That's
like
right.
everybody
Yeah.
who really thought about it already knew it, but I don't know if there's
That's
some
kind of how
standard
they.
reference.
Yeah, they indeed they say that in the paper as well, that it seemed kind of like folklore. And okay, so the result is, so in what I described so far, we have this prefix predicate that is indexed by the height of the tree, essentially, and that was a natural number. Well, if you just change that from being a natural number to being an ordinal, so you can go much higher, well, then you don't need continuity. That's the sort of the short thing. Of course, now you have to be careful about, well, what does it now mean to define? So now you need to define this predicate also for the limit ordinals, but that you do as when this prefix predicate for limit ordinal, um, lambda, let's call it, that holds if there exists something smaller than lambda for which it holds.
Yeah,
And there I
it's
just
kind of hard not to come up with that definition.
That's right. Exactly. I think that when you're working with those things, I mean, you would go in that direction. And so that actually means that what Dafny does is for these inductive and conductive predicates, that is least and greatest predicates, Dafny defines automatically the prefix predicates underneath, and they're defined, they're indexed by ordinals. And then when you do proofs of these, you actually do, I mean, you do induction, but that kind of induction is often called transfinite induction, which is, I don't know why it's called that really, it's just induction. But anyhow, people call it transfinite induction. And this sits on top of a first order SMT solver that gives automation. So for many of the simpler problems that you would do in this way, Dafny actually just does it with no proof required from from the user. It just spells it out. But of course, when you get to more difficult things, you have to do the proofs, of course. But so it's a tower of things that comes down to there, but it comes down to something that seems so higher order and inductive and transfinite and ordinals and fixed points and whatever, and it sits on top of a little SMT solver in the end.
Right.
So,
But yeah, in some sense, yeah, at the end of the day, you've justified this principle, right? But the principle was always there in some sense, which
right,
is you get to pretend that these proofs are data
right.
if you want,
If you want to, right,
and these are the rules. And then
right,
somehow the ordinals are there to reassure you that all
That's
this
right,
stuff is true.
right,
But
exactly.
yeah,
Yeah,
but it's just the justification. You can kind of sweep them under the rug
right.
for most things.
Exactly right. And Daphne tries to do that so you don't kind of see it. It actually, when you write such a proof in Daphne, or when you write proofs about like the co-inductive things, for example, it kind of looks just like you like an undergraduate wrote the proof and forgot that you had to prove termination. I mean, it just
Right.
seems to like very casually called inductive, but it actually the mathematics underneath comes through, and that's something that well, more recently, this must be at least a decade ago, I guess. Um, Alexandra Silva and Dexter Cosen wrote a paper on conduction that where they were trying to say, hey, conduction is never taught because it's looked upon as being so complicated, but it really isn't. So they're trying to show it the easy way, and that actually corresponds very much to what is in Dafny in that sense.
Cool.
Uh,
Cool.
right. So yeah. So this was the story about those. So I mean, if any listener actually happens to look at that paper, actually, I was quite happy with that paper, by the way, how it describes the mathematics. But that paper was written before I knew the Cousot and Cousot result. So the paper talks about it only uses natural numbers and it talks about continuity and in the Dafny tool you can choose to use the naturals if you want to, and then it's going to enforce continuity. But the default case is that it uses ordinals, and then that doesn't matter. So
That's very cool. Yeah. I guess because of my PhD, I'm a little bit fascinated by this ordinal trick. I mean the proof is really simple, right? Basically you look at you look at this definition for every ordinal, right? So this kind of class level. And this is a very common trick
mhm,
in logic. So for every ordinal, you can keep applying this function that grows your predicate.
mhm,
And at some point, you just think about the cardinality of things, and like there are too many ordinals for this
mhm,
to keep growing indefinitely. So at some point, you kind of you've run out of space, and
mhm.
you have to be a fixed point because there's nowhere else to grow.
Right,
And so all you need is just the fact that there are really big ordinals,
right.
and those perhaps should not be contemplated too closely because of the effect it has on the brain.
That's
But
right. And the
the
death rate of such scientists is
yeah,
sort of
but But as a mathematical
Mhm.
justification, this is almost trivial, right?
Yeah, right,
It's a couple lines of proof of just
right,
you've run out of
right,
space.
right.
So I'm kind of fond of, maybe that's why it's a folklore result, is because it's almost too easy if
Uh-huh.
you're familiar with the tools involved.
Right. Yeah, I don't claim to understand every piece of mathematics in the Cousteau and Cousteau papers, but this one I read very carefully and felt like, of course, it takes time to go through all the details, but I felt like I understood it. Um, right. With that, there is I mean, for this to work out, the ordinal that you use needs to be larger. I kind of like to think of it as larger than anything else that's around. That is, it should be larger than the cardinality of something else, which is also kind of funny to mix cardinality and ordinals in the same sentence
Yes.
somehow. But the paper does it justice what it says. So there, I do believe that. That Daphne does that soundly, but actually, I'm not sure that it's dicey because the if you allow such an ordinal to be a type that you quantify over, well, in that case, then you would need an even larger ordinals for these heights of these trees. And so Daphne restricts what you can do with the ordinal type. In fact, the type ordinal is all capitals ordinal,
Yeah,
which
which
is
is always a sign that something's dicey.
exactly the only keyword in Daphne that has any capital letter, and this one has all of them. But it's because it is special in that sense. But there could be errors in that, and I mean if someone is really into these things and would want to check that in some way, I've sort of dangled that carrot in front of
Well, that's tempting. Like I said, I've thought mildly about these problems.
Mhm,
There was a proposed. I mean, Agda, of course, has ordinals as well,
mhm,
in almost exactly the same way, right? Where you get to use them to
mhm,
define certain functions and certain data types.
mhm,
And Rock, for a while, as I was doing my PhD a while back,
mhm.
seriously considered adding these,
Oh,
and it ended up just not happening for various reasons. But the meta theory was thought about pretty carefully.
mhm.
Um, and so yeah, so probably the tools exist to
Right. Uh-huh.
answer
Yeah.
this question, but
Yeah. So anyhow, yep, that's the end of the story there. But
yeah, I love this story. Like it's almost custom made to be relevant to me, to my interests. Um,
but, yep.
I also, let's see, one thing I wanted to mention because it just tickles my brain. The the Booleans, right? So it's very, so programmers know that there are only two values of the Boolean type,
Mhm.
and therefore, you know, this very finite thing, and it doesn't make a sense to do well-founded induction over the Booleans unless you only do, you know, at most two steps or something.
Yeah.
Um, but like I said, in the calculus constructions, you know, there are no, yeah, the Booleans aren't really like that interesting, and proofs are just ordinary data types, you know, that are completely indistinguishable from data, you know,
Hmm.
lists and ints. Um, but I guess the intermediate perspective would be um, anything anything that can be a truth value, right? It, you know, can replace the Booleans effectively everywhere.
Hmm.
And that could be a Boolean algebra, but those can be huge, right? They can be very large. And so seeing, you know, multiple steps of inferences in there, perhaps, you know, even an infinite number, is
Hmm.
not absurd, right? It's a very reasonable thing to see in a general Boolean algebra.
Hmm.
And then the Booleans are just a special case of Boolean algebra,
Hmm.
perhaps even a, yeah, boring one, right? Or because in yeah, because in real life, okay, but I'm not going to push this point too hard.
Yep.
The truth value of a proposition is very much not evaluate a function and see if it's true or false, right? It's use
Right.
these complicated reasoning steps, and so it feels like in real life, the truth value of a proposition is not just zero or one. It
Hmm.
is contains a lot more. And
Hmm.
so I wonder if there's some perspective where instead of the Booleans, you look at something much richer, and
Hmm.
then looking at infinite sequences or finite sequences within that realm is not so absurd.
Uh-huh, right. Yeah,
Sorry, that was an aside I felt compelled
right.
to
That's
make.
great. Yes, good.
Um, okay, maybe do you have some more higher level remarks? What what are exciting things you want to think about next, maybe in this
Um,
realm? We've talked about a bunch of interesting things, but
mhm. So let's see. Yeah, so one thing that I'm currently working on is a new intermediate verification language that is think of it as a new version of Boogie. I mean, Boogie is 20 years old and or thereabouts, and so the new one I'm calling B3, and
that's exciting.
right that yeah, I won't go into what this does. But what B3 tries to do is there have been a number of things that over the years have been more awkward to encode into Boogie, and B3 tries to make that better. And then also pay attention to um, uh, things that would make the verifications more stable with SMT solvers. And yeah, that's one thing I'm doing.
Right, because at the end of the day, yeah, we want to abstract away from it, but
Mhm.
there are
Yeah.
practical considerations.
Yeah. But exactly. So, but another thing that I'm well, that's going through my mind is uh, how to. I mean, if one were to take the lessons learned from Dafny and from other programming language designs, including, I mean, Rust and so forth. If one were to design such a language again, what would it look like? Um, and I mean, such a there have been, I mean, when Dafny was designed, when I designed Dafny was, um, it was meant to do an experiment with a particular way of specifying programs with in the heap. And I was encoding those things by hand in Boogie, and I just got tired of doing it by hand for my experiments. I thought, well, I'll just write a little tool that's going to do it for me. And that was Dafny, and then, well, Dafny sort of grew. Um, and but I think if I were to attack that now, that is, if I were to think about it and thinking about, I mean, how many years Daphne has been around, to if I were to take I mean, a long-term view of saying, well, what is going to be, I mean, if the next language is going to live as long, um, which of course most languages do not, but if one were to take that view,
Yeah.
then what would it look like? And I think that. What's always been special about Daphne was that it was designed for verification to begin with. But I think it's time to rethink that a little bit. That is, it should of course support verification, and that should be in there. But we know many more things of how to do that. But what Daphne has done poorly, and or at least took it a very long time to get to, is, well, what about sort of a package manager? What about some um, a standard library? What
Yeah,
about,
yeah, yeah.
I mean, getting it easily in various ways? What about, I mean, testing tools or like a Java doc tool and, I mean,
Yeah, yeah,
documentation?
the quality of life things that you
Exactly, right.
expect.
Because they were not there, and they because the way that Daphne, I mean, came into being and so forth, those were not the concerns. And I think, and of course, if you pay so much attention to all of that, you will never get to actually the language itself or the whatever. And but I think it's really worthy of
Yeah.
consideration. And
Remembering that if you want a language to be useful, it's
mhm,
going to need these things eventually.
right. And I mean, now with I mean, going to I mean, with AI and things like that, right? What one would want like an interface to an AI agent, so that and maybe if one designs the language with those sorts of things to begin with, maybe one could, I mean, do something that's interesting, and both interesting from a scientific exploration point of view, mathematically and so forth, but also that could be, I mean, a very useful language in because as I said, I mean, in the context of Java, Java was difficult to write a verifier for because there's so many things in there, like the side effects and things that you have to like redesign in a different way, or if you want to have the immutable things in the language, you have to add them in some way, or I mean, in addition to, of course, adding pre and post conditions. So Dafny had all the right starting points there, and there have been other languages that have done that, F star, for example. And but then, yes, starting with the sort of quality of life and what's expected, and actually, I would also be quite interested in having that language be something that would compile to like native sort of like low level thing, this sorts of programs that you would write with C or Rust. But of course, it would be, I mean, even safer than Rust in the
I
sense
see.
that,
You're saying that you want that to be the target operational
or at
semantics.
least I would actually love it if it could be both that and something that's garbage collected, and you would know as the programmer which one you're using where. I don't know. Yeah. So I mean, you asked about, I mean, what I'm
Yeah,
thinking. I
I
mean,
I think it's exciting. I think it you should always have something to look forward to or to be excited about. I think
right,
otherwise, yeah, that's excessive pragmatism is dangerous, I think.
right. Yep.
Those are great things. I don't know. It's exciting.
Great.
This was extremely fun, I have to say.
Right. Was, yeah, a
I
lot
don't
of
know.
fun.
I
And
mean,
my lunch is still sitting here, so I'm
oh my gosh, I
no,
feel
just
so
because,
bad.
well, no. I was just pointing out that it was so much fun for me as well. So
Oh,
I
okay.
will. So this is great.
Yeah, well, I'll let you get to your lunch, but I don't know. I don't, you know, podcasts come and go, yeah, as programming languages do, perhaps faster, but you are always going to be welcome on this one.
Well, thank you very much.
I
Right.
hope I hope I'll see you again, and
Yeah.
I'll try to build some list of things you mentioned and put those in the comments. But
Oh, great. Yeah. Yeah. Thanks. Right. Yeah. This was fun. Thank you very much for having. I
all
mean,
right.
actually, I very much enjoyed our conversation. I hope that there are listeners out there who got something from it as well. So
I hope
great.
so too. And to all the listeners out there, until next time,
Yeah.
take care.
Yeah. And program safely.